turning wind into energy. These high-tech, high-output turbines are powering the switch to green energy worldwide. But building and installing these ever larger wind turbines poses an enormous challenge.
We can make them larger. That makes them more efficient.
As the turbines grow, so do the factories in which they're built. State-of-the-art robot technology is used to build the enormous nacelles and powerful generators. The rotor blades are especially large. They're more than 80 meters long and weigh 20 tons and are molded in one piece.
One blade is larger than the wingspan of an A380.
To bring the enormous components to remote locations, the engineers need special ships, high-load transporters, and mega cranes. Without them, the wind turbines couldn't leave the factory. The crews need nerves of steel when they assemble the wind turbines on site. Even a tiny error can have deadly results.
We don't necessarily have more problems, but they're more dangerous and more deadly.
Wind turbine manufacturing is booming around the world. The industry is driven by a single goal:
bigger and longer and more heavy.
A giant wind turbine is being built. A high-load transporter is delivering the first concrete parts. 10 specialists will build the first of a total of 24 tower elements, each weighing at least a ton. At the Falkenthal wind park near Berlin, 11 giant wind turbines can generate up to 530 megawatt-hours a day under optimal weather conditions. But that's not enough. Over the next weeks, an E82 wind turbine will be joining them here. The turbines measure 138 meters from ground to hub and have a rotor diameter of 83 meters. Under good wind conditions, they can produce up to 5,000 megawatt-hours per year, enough to meet the annual energy needs of some 1,200 households. The first step is laying the foundation. Made out of 75 tons of steel and 700 cubic meters of concrete, it extends 4 meters into the ground and weighs several thousand tons. If the ground can't support such weight, the foundation is further anchored with 40 concrete pillars that extend 15 meters into the ground. The crew has already placed the first section of the tower onto the foundation. Now a special crane is hoisting the second ring onto the base. 3 crew members push the second ring, which weighs almost 120 tons, into position. Two iron centering pins help position the second segment flush with the first. The 2 segments must maintain tolerances of just a few millimeters. 15 minutes later, the second ring is in place, and the tower has grown by 4 meters. Inside the tower, the crew also moves higher. They stand on a platform that has 6 legs, which adjust to the tower's diameter. Every time the tower grows, the crane pulls the platform up another 3 meters. Then the platform is re-anchored onto the interior wall. Outside, the rest of the crew is preparing the third ring. The crane suspension system uses several orange heavy-load slings to hoist the tower sections. The number, length, and strength of the slings vary according to the nature and the weight of the load. The crew carries out precise calculations, taking all the various factors into account to make sure that everything goes smoothly.
People's lives are at stake. The crane operator's view might be obstructed, so they're guided by radio. The tower's first rings are very heavy, more than 100 tons, so we use a floating ballast.
The floating ballast is the massive counterweight that stabilizes the crane and keeps it from tipping under heavy loads. It allows the 565-ton crane to lift more than its own weight, 600 tons. The crane's boom is 126 meters long. It takes 3 days just to set up the crane. There's a wind meter at the tip of the boom. According to safety regulations, wind speed can't exceed 9 meters per second during this part of the operation. Even a tiny amount of swing in the load could be extremely dangerous. Today, the wind speed is 3.6 meters per second, so the work can proceed. The crawler crane lifts the ring, and the crew shifts it into position. They've built dozens of wind turbines around the world and know they're on a tight schedule. Over the next 8 days, they'll add another 18 cement rings, reaching a height of 83 meters.
Right now, the segments are being stacked. They won't be joined together until the steel section goes on. We used to glue the segments together, but we stopped doing that years ago for reasons of cost and efficiency.
Right now, the rings are being placed one atop the other. Their enormous weight makes the tower stable. Later, the crew will mount 24 steel cables, each as thick as an arm, into the structure. The cables will lash the tower segments tightly together. Now it's time to remove the work platform. Its legs are retracted, and the crane lifts it out of the tower with the crew still on board. At this stage in the construction, the diameter of the top segment is still large enough to permit the control cabinets and electrical equipment to be lowered into the interior. The next set of turbine parts are almost at the construction site. 12 trucks are just a few hundred meters from the tower. They are carrying the next 4 rings, each of which is made up of 3 segments. In record time, the crew have attached the slings and unloaded the trucks. The first of the 3 concrete shells are positioned on a mounting star. Casting the concrete into a single piece and then transporting the 100-ton colossus would be inefficient and very expensive. That's why it's assembled on site. The crew unload the second shell and place it on the mounting star. They use chain hoists to pull it into the correct position. The third concrete shell completes the ring. The crew begin to shift all of the parts into alignment and screw them together.
We want them to be flush so that the screws will fit into the holes. So we have to pull this one out.
With hydraulic pumps and chain hoists, the crew tug the concrete shells into place, centimeter by centimeter. Then they fix the segments together using 30mm steel screws. In less than an hour, the crew has assembled the 4th ring. The huge crane hoists it into position, where it will remain for about 2 decades. Then the wind turbine will be refurbished or replaced. The minimum lifespan of 20 years is also why manufacturing and assembling the turbine is precision work. This factory in the town of Brande, Denmark, produces more than 1,000 on- and offshore wind turbines a year. 3,000 skilled workers use high-tech robot technology to assemble the multi-ton gondola, as the cover of the Nacelle is called. Wind turbines built here are found in more than 90 countries around the world. These large factory halls are where nacelles used in the SWT-7 wind turbines are built. These wind turbines are up to 165 meters high and are intended for offshore use. Their rotors are 154 meters in diameter. Each wind turbine has a capacity rating of 7 megawatts a year, more than enough to power 7,000 washing machines. A crew of 65 is building the offshore giants. The 3,000 square meter production line can produce 4 nacelles a week. Demand for these turbines is rising, as are the technical demands being placed on them.
The biggest challenge in the industry is to constantly improve the technology to bring down cost. The expectations from all our customers and in the end from society is that we can get wind energy to a level of what other fuels cost. First of all, you can make them larger. That makes them more efficient. But then we also work on more advanced aerodynamics for the blades, lighter structures. But basically we work on everything.
Building offshore wind turbines is a very complex process because they're much larger than their cousins on land. But their enormous rotors also generate more electricity, and the higher wind speeds over water are converted even more efficiently into electricity. Erecting wind parks on the open sea requires special ships, jack-up platforms, and heavy-duty floating cranes. To withstand years of wind, waves, and inclement weather, offshore turbines need to be supported by a massive foundation. Depending on the depth of the water and the prevailing currents, up to 4 massive steel pillars are driven up to 30 meters deep into the ocean floor. This anchors the offshore turbines, which weigh several hundred tons. Germany built its first offshore wind parks in 2004. Since then, it's been adding about 100 offshore turbines a year. Unlike their Scandinavian and British counterparts, German offshore wind parks are not situated near the coast. Instead, they're located more than 12 nautical miles out at sea, meaning at least 22.2 kilometers from land.
Wind energy has become quite competitive because it's been around for 20, 30, in some places 40 years, and we keep getting better. The turbines have grown larger. They started out the size of a dining room table. Now a single blade is larger than the wingspan of an A380. The technology keeps getting better and better, and the costs keep getting lower. That's why wind energy is in such demand around the world today and why it's so useful.
The components for a giant offshore wind turbine have just arrived at the factory. This 30-ton mainframe is the heart of the turbine. The cast iron structure will join the tower to the oversized nacelle and rotor, which will be able to spin. The mainframe is equipped with an enormous gearbox so that the nacelle and rotors can turn as needed. At the next station, the crew will install 16 yaw gears. Each of these electrical motors turns a yaw drive that meshes with the gearbox in the nacelle. That allows the rotor to turn and the nacelle to swivel toward the wind. Sensors are placed at various points in the nacelle to measure vibration, wind direction, and wind speed. The 16 electric motors turn the 80-ton nacelle as efficiently as possible toward the wind. When the nacelle turns, the rotors must stand still. The SWT-7 wind turbine can handle wind speeds between 2 and 25 meters per second and convert that energy into electricity. At higher wind speeds, the unit shuts off for safety reasons. These high-tech electronic boxes keep the nacelle properly oriented in the wind. The boxes contain complex sensors and the control systems.
The top boxes in the wind turbine in the nacelle are electrical panels with electronic equipment that controls the motion of the blades and does some measurement, so a lot of sensors are there. We measure temperatures, we measure wind speed, wind directions, vibrations. We measure the pitch angle, so how the blades are positioned. We measure the yaw angle. So a whole lot of parameters that are all fed back to our monitoring center.
The company has installed some 11,000 wind turbines around the world. Data from the turbines is transmitted through fiber optic cables to the diagnostics center in Denmark. 85% of disruptions can be fixed remotely. The data also supplies information about the wind turbine's efficiency. This nacelle has been equipped with all the necessary electronic sensors and control elements. Now the crew begins assembling the sidewalls. They're made of glass fiber reinforced plastic, or GFRP. This composite material, which is light in weight and extremely strong, is also used in airplanes. Older wind turbines were made of aluminum, but metal is too heavy for today's massive structures. Then the crew fasten the sidewalls using 222 screws on each one. The finished nacelle weighs as much as 4 school buses. But before it goes to the client, it gets a thorough checkup.
It is crucial that quality is in order, because even a minor mistake can cause the wind turbine to shut down. We need to make sure that a turbine is running. Mounted on the ocean, then you need to go out there. It's quite expensive to have a turbine that's not running.
The nacelle is now ready to head to Germany. We return to the Falkenthal wind park. Over the last 6 days, the wind turbine's tower has grown to 22 rings, totaling 80 meters in all. Today, the crew will mount the final 2 segments. 3 crew members board a work platform that's quite a bit smaller than the one used to mount the bottom rings. The tower is narrower at the top than at the bottom. The opening at the top is just under 2.5 meters across. After nearly 10 minutes, they reach the 80-meter mark. The crew remains in radio contact with the crane operator as they shift the cockpit into place. Then they give the order to lower the platform and anchor it to the tower. It's routine work, but they remain alert. This far above the ground, a single mistake can spell disaster.
Things don't go wrong more often, but when they do, it's more dangerous, more deadly. 100 meters above ground, anything that falls can do a lot more damage than when you're on the ground. The crews get medical checkups to confirm that they're fit to work at these heights.
During training, the crews also receive instruction on how to safely carry out a rescue operation in the event of an accident or fall. Every 6 months, they also receive a medical exam to ensure they're capable of working at great heights. The crew attaches the safety cable and removes the cables from the crane. 20 minutes after leaving the ground, they're 80 meters up and ready to work. They'll be on this small platform for 3 or 4 hours. There's no toilet, no heat in the winter, and no shade in the summer. Just cleaning the stop of the uppermost ring is hard work. The ground crew has an easier time of it. They're preparing the next concrete element for installation. The underside of the ring has to be cleaned, and 2 centering pins are released into position. The crawler crane hoists the concrete ring to the top. This one is 42 tons, a lightweight compared to those at the bottom. But that also has a disadvantage. The lighter the load, the more likely it is to swing when raised. The crane operator has to be extremely skilled and relies on precise instructions from the platform crew. The crew begins to carefully maneuver the segment into place. 20 minutes later, the concrete ring is in place at the top of the tower. The crew are now 83 meters above ground. They begin opening the contact channels. 24 shafts extend down the outer wall from the top to the basement. They use a pendulum to make sure that each shaft is clear. If it's blocked at any point, the steel cable won't descend. While the crew mount 4 threaded bolts, the next segment is waiting on the ground. It's solid iron, not concrete. Like a kind of cork at the top, it will be attached to the 24 steel cables that will extend all the way to the ground, squeezing the segments together. Once the screws are in place, it's time for a lunch break. But first, they have to climb down the ladder. They attach their harness into the ladder's fall arrest system. Then they detach the second lifeline from the work platform. 80 meters and almost 300 rungs. Descending the ladder requires strength and stamina. The tower grows wider toward the bottom, so the descent is also at an angle. The crew member's body weight pulls them away from the ladder. 6 minutes later, all 3 are safe on the ground. While the platform crew takes a break, the others unwrap an enormous reel holding the wound steel cables. Each reel holds 4 85-meter cables, each made of 9 individual strands of steel. They'll eventually extend from the top to the bottom of the tower. Right now, the crew attach the cables at the foundation. Then they'll be pulled up through the shafts. Another special component is on its way. This is the motorized unreeling device that will unwind the cables on the reels so that they can be extended through the channels. The cables are so heavy that they can't be unwound by hand. The crew board a platform basket, which is raised to the top of the tower. Climbing the ladder would be too strenuous and time-consuming. But the way up still takes nerves of steel. The fall protection cables are detached, and the crew returns to the platform. The 5-ton cable reel, now attached to the motorized unreeling device, is raised to the top of the tower. 2 crew members begin unraveling the first steel cable. 1 level below, the 3rd crew member feeds it into the channel. Then the rest is unraveled. It extends down through the wall of the tower, all the way to the basement. Then the mounting bracket on top of the cable is fastened with 6 screws. By the end of the day, 24 steel cables extend from the top of the tower down to the basement. Later, the crew will use a special procedure to tighten the cables. That will ensure that the final structure is stable. The facility in Brande, Denmark doesn't only build nacelles for offshore wind turbines. Every week, 18 high-tech nacelles for onshore wind turbines are also made here. SWT-3 wind turbines are up to 142 meters tall and have a rotor diameter of about 100 meters. With a maximum speed of 19 revolutions a minute, it has a capacity rating of 3.2 megawatts. The crew works at a set pace. Every 4 hours and 20 minutes, the assembly line moves forward 1 station.
We have a whole line here, and for each station we have 4 hours and 20 minutes to do the assembly process that we need to do on this station. If the takt is not working, then we will need to look into what is the problem. It could be quality issues or missing parts. When that happens, we need to contact our support functions to get them to help us and make a decision on what to do then. Losing takt will also mean that we will lose our money. It means that we later on need to do overtime to catch up and probably reschedule some of the deliveries that we have.
This compact nacelle has been in series production since 2010. One of its selling points is that it's assembled here in the factory and not at the construction site. There are currently 2 ways to generate electricity out of wind. In the first option, the rotor's rotation is passed on through a series of gears to a small generator. In the other, the rotor directly powers a large generator. Wind turbines that use gears have a longer nacelle, which holds the gears. A direct drive wind turbine has a comparatively shorter nacelle. The Brandenburg factory specializes in direct drive wind turbines. Their generators operate much like an oversized bottle dynamo on a bicycle. An enormous copper coil is located inside the generator. When wind turns the rotor, magnets are spinned around the copper coil, which generates electricity.
We introduced the technology in 2007 on the first test machines, but it's only in the recent 5 years that we have really reached high volume in this technology.
The copper ring is built out of 6 massive parts. Copper is a metal with very high electrical conductivity. The coiled copper increases inductance. Copper is also a soft metal that is easy to work with. The crew is now fitting the so-called stator in a special housing. The generator housing is then inserted into this machine. Inside the machine, 4 robot arms install magnets into the drum surrounding the copper coil.
We received the magnets, we call them cold, so they are not magnetized. The robot picks a cold magnet, magnetizes it, and puts it into the finished generator. The magnetic strength in this cell here is very, very high, so no humans can enter there. Once they are in the generator, they are not dangerous anymore.
The cold magnets are coated in a special alloy that helps protect them from wear and tear. The high-tech robots install a total of 648 magnets in the generator. Then the generator is placed on a platform truck, which transports the 3 million watt generator to the next factory hall. This is where the generator will be installed in the nacelle. First, the crew attaches a large transport frame to the ceiling crane. A custom-built prong device makes it possible to move the generators safely. Here in this 3,000 square meter factory hall, a nacelle for an SWT3 wind turbine is assembled every 4 hours. When the direct drive generator is docked and screwed into place, the entire nacelle weighs 73 tons. This factory belongs to one of the world's largest wind turbine manufacturers. It costs almost 3 million euros to build one of these turbines. 3 different types of nacelles are built here. A heavy truck brings it to the harbor in the Danish city of Esbjerg. From there, the units are shipped all around the world. The freighter also transports the enormous nacelles to Germany. At the Falkenthal wind park near Berlin, preparations for the arrival of the nacelle are underway. But before the nacelle can be raised to the top of the E82 wind turbine, the crew has to install the last two steel sections. Two cranes are needed to lift the steel sections. That allows the crew to lift the pipe while making sure that the delicate ends of the section don't hit the ground. The fog and approaching dusk make the work more difficult. Wind could also pose a problem. At wind speeds of more than 8 meters a second, this stage of the work would have to be postponed.
If the crane tried to lift 58 tons at a wind speed of 10 or 12 meters per second, the steel section would start to swing. The crane could even tip over. We'd be risking the workers' lives. There's no way to know where the crane would land if it fell.
Despite the less than optimal conditions, the steel section is raised without a hitch. The crane hoists the section to the top of the 83-meter tower. The tower is another 25 meters taller. The work continues without a break. The next steel section is raised. It's 28 meters long and weighs 42 tons. After it's in position, the wind turbine's tower is finished. The 136-meter tower is made up of 24 separate elements. The crew is now preparing the high-tech nacelle for the last stage in the process. This type of nacelle weighs 19 tons. The crew have to work quickly. It's getting dark and it's getting foggier. The operation gets underway. Under optimal conditions, it takes a month for a new wind turbine to be ready to go online. The crew are working under difficult conditions today, but time is still money. They've already spent 10 days building the tower. In the last few hours, they installed the final two steel sections. Now they've attached the nacelle onto the tower, 136 meters above ground. They'll have only one day to install the enormous rotor. Another factory in the Danish city of Aalborg makes rotor blades for wind turbines. 1,300 workers produce about 2,000 blades here a year. A number of different factors play a role in their construction, including their lifespan, their noise emissions, and especially their performance.
Here in Plant Aalborg, we are doing both onshore and offshore blades, and it's integral blades. That means it's actually one-piece blade. We are doing in the lengths between 53 meters up to 81 meters. And we do in a round of 30 to 40 blades a week here in this factory.
Each blade starts out in a huge mold, much like this one. That's also true for the largest blades built here in Denmark. At 81 meters, it's one of the longest rotor blades in the world. This fiberglass matting is the raw material. That's what the packers, as the crew at this station are called, use to pack the giant mold.
It's easy to handle and very easy to form in our molds, so we don't have any issues by laying them down or straightening them out, if that's what we needed.
The fiberglass strips have a special woven structure, which makes for an exceptionally sturdy blade. The matting must be laid out with no wrinkles or air pockets, which would have a negative impact on the material's structural properties.
If you pull it, it's very stiff, and just with a little bit of wrinkle, you can pull it over, not much strength.
The packers lay 500 strips of fiberglass matting into the mold. They need to overlap in a specific pattern and be placed at set distances from each other. Then the finished blade can withstand all sorts of loads and weather conditions. The interior of each blade also contains a connecting beam, as tall as a man which provides additional stability. To install the beam, an overhead crane moves an enormous steel frame over the mold. The frame holds the wooden core. For safety reasons, the packers have to wait until the frame is stationary. Then they can remove the beam and fasten it into place. Wind turbine rotors are growing ever larger. Longer blades can generate more electricity, which reduces the number of wind turbines needed to meet demand. This blade will be even longer than the wingspan of an Airbus A380. Next, the crew install a lightning rod. Then a foam core is placed in the mold. It will be topped with another 500 strips of fiberglass matting to form the top of the blade. The foam will then be removed, leaving a hollow and lighter weight blade. This makes it possible to form the blade as a single part. After the packers have covered the foam core with a layer of wood, they can begin laying the fiberglass panels that will form the top of the blade. Now all of the parts of the blade are in place. The overhead crane moves a massive steel shell in position and closes the mold. The inside of the shell is fitted with a system of pipes. All the air inside the blade will be sucked out through the pipes, and then the structure will be filled with a two-component resin. A special pump and mixing unit injects 8,300 kilos of resin and the hardener into the mold.
The resin and hardener flow through these tubes into this mixer, which mixes the two components at a specific ratio. That's how the epoxy resin is made. And it continues over here. The mixed resin flows through these tubes. The vacuum sucks the epoxy resin into the mold. The form is also heated at the same time. Its temperature increases slowly, about 0.2 degrees per minute, until it reaches 92 degrees Celsius. That takes about 7.5 hours. Then the blade is left to harden another 2 hours at 85 degrees.
The rest of the air is removed through these hoses. The resulting vacuum causes the rest of the epoxy resin to move into every nook and cranny of the mold. That way, no air pockets can form inside the blade, which helps ensure maximal stability. 9 containers of epoxy resin flow into the blade. Once the entire mold is filled, it's heated. The mixture of synthetic resin and hardener binds to the fiberglass mats. Then the blade is left to harden. The end result is one of the largest rotor blades in the world. The blades used in the E82 wind turbine in Falkenthal are some 38 meters long. They're brought to the construction site on 3 special trailer trucks. Two cranes are used to unload the rotor blades. That way, the 8-ton blades can be lifted from both sides, which prevents accidents and damage. The blades are first set on the ground. Modern wind turbine blades have a sawtooth edge along a portion of the blade. It makes the blades quieter and more aerodynamic, which boosts efficiency. The design was inspired by nature, the trailing edge of the wing of an owl, which allows it to swoop quickly and silently on its prey. Next, the 3 blades are attached to the rotor's hub. When the unit is running, this is what will transfer the power from the blades to the generator. A hook is attached to the blade's center of gravity. That makes it possible for a single crane to lift the blade while keeping it parallel to the ground. The blades are attached to the rotor hub at an angle of 120 degrees. The hub has been carefully positioned. When the blades are attached, the crane will be able to lift it and turn it to the vertical position in a single motion so that it can be lifted to the top. It takes about 5 hours for the crew to attach the blades to the hub. Then the 56-ton rotor star is ready to go. But first, we return to the factory in Aalborg. A new blade has just been made. The packers laid out 500 strips of fiberglass matting in an enormous steel mold. The strips were laid out in a special overlapping pattern to ensure that each finished blade would be strong enough to withstand heavy wind. Then a massive ceiling crane placed a connecting beam on the inside of the blade to help stabilize it. A temporary foam core filled the inside of the blade. That was topped with a wood panel, and finally with another 500 fiberglass strips. Then the top of the steel mold was placed over the structure. Air was pumped out of the structure to generate a vacuum. The mold was filled with a mixture of resin and a hardener. The mold containing the fiberglass and epoxy resin mixture was heated for 10 hours and allowed to harden. The end result was an 81-meter-long blade made out of glass fiber reinforced plastic, or GFRP. The material is robust and light in weight, but it also has some disadvantages. Even small air pockets or indentations can weaken the blade. That's why the crew is now making sure that the material is perfectly solid and smooth. Any flaws are removed with a grinder, and the resulting holes are refilled with new GFRP until the blade is solid and smooth. Next, the rotor blades go to the painting line. They first get a primer coat, which is then topped with a special protective coating. The polyurethane varnish creates a hard-wearing surface that can withstand immense mechanical stress. This mechanical stress increases proportionally to the length of the blade.
So it goes towards longer, bigger. And then you need to think about the nature laws, how you bring it around in the production, how you manufacture it, but also how you bring it from the plant actually out to the sites, either on ships or lorries, and how do you actually bring it on the site and install it. You need also big cranes, installation ships. So there is a lot of parameters that you need to be thinking about and thinking new ways to be able actually to fulfill and meet these new challenges.
Next, the blades are subjected to various fatigue tests, which can take up to 12 weeks. The engineers subject the blades to extreme bending and torsional moments over long periods. In the simulations, the blades must withstand the same force that it will be exposed to over its entire lifespan. Not every blade is tested in this way, but a random sample of blades receive rigorous testing, as do prototypes and new designs.
Most blades are tested for some loads equal 25 years of lifetime. It can also be 20 years, but mostly 25 years. We can also do extended test programs where we test the blades to double lifetime, so it can be a pretty long time. But a complete test program for a blade can be up to 1 year.
The blade is attached to a special test tower. In the middle of the blade, a multi-ton weight causes the blade to oscillate. Depending on the size of the blade, up to 400 sensors measure various parameters 25 times per second around the clock.
I've been there for almost 7 years. I think I've seen only 2 blades failing in a fatigue test. It's so rare that the blades come down because we monitor all the data so closely that we will find the errors before they actually develop to something serious damage.
The enormous blades from Aalborg are amongst the largest in the world. At 81 meters in length, they have a surface area of 20,000 square meters. Blades of this size produce offshore wind turbines with a capacity rating of 7 to 8 megawatts. At the Falkenthal wind park, the rotor star has been assembled. The next step will be a complicated one. The crane will lift the rotor from the ground and then turn it upright in the air, just a few meters away from the waiting tower. For safety reasons, the maximum wind speed during this maneuver is 6 meters per second.
You can see the size of it. The diameter is 83 meters. The crew have to stand nearby because we need to tip the star. We lift the star, and then the star is tipped upright so that it can be raised.
The crane slowly lifts the rotor star. A 56-ton rotor the size of half a soccer field will now be moved to a vertical position. The rotor is hanging on a special hook called a banana. Its curved shape allows the entire rotor star to hang in perfect balance. Only a small amount of force is needed to tip it. While the crane lifts the star, 2 crew members pull it toward the tower. The enormous rotor star slowly moves from a horizontal to a vertical position. Meter for meter, the wind turbine's propeller is slowly raised to the top. 2 long cables are attached to the blades, which the crew use to maintain an even keel. An hour later, the enormous rotor star has arrived at the Nacelle, 138 meters above ground. The crew then attaches it to the generator with screws. After 4 weeks of work, the new E82 wind turbine is finally in position. Over the next few days, the wind turbine will go online. When the wind reaches a speed of 2 meters a second, the turbine will start automatically and generate green energy.
We have an immense and growing need for electricity due to a rising global population, the expansion of the grid and electric vehicles. Cheap renewable energy from wind power is ideal.
The first wind turbine was built almost 130 years ago. Since then, people have been harnessing the power of the wind as a cheap, powerful, and unlimited source of energy. Today, wind turbines are high-tech industrial installations. Their enormous nacelles contain giant copper coils. State-of-the-art robots install enormous magnets in them. Nowadays, wind turbines are made on the assembly line. The rotor blades are made with the help of enormous steel molds and special robust materials. Thousands of production steps are needed to bring a new wind turbine online. Once it's finally in operation, nature and technology work hand in hand to generate energy out of wind.